Hey, everybody. I'd love to introduce Nils Thuerey from Technical University of Munich or München. He is, I guess, trying to automate science and try to make our simulations amenable to a proper optimization of their internal structure. So, yeah, welcome.
Thank you very much for the introduction, Greg. Thanks for the invitation to speak. And right, I want to dive into one of the more recent topics that keeps us busy. So it's a bit more preliminary than some of the other stuff I used to talk about, but I think it's quite interesting. And these diffusion models, I'm sure everybody has heard of, are actually also quite interesting for simulations and the scientific computing field. And as such, I want to focus on the combination of diffusion models and in particular simulations that are differentiable. So let me start a bit more broadly. Yeah, I should also mention right at the beginning, simulations are a big field, so I should mention that I'll be mostly looking at dense, pretty regularly sampled, fairly smooth phenomena, so less particle physics or ray-like things. So fluids are typical applications. Yeah. I used to start talks like this trying to convince people that deep learning is worth looking at. By now, I think it's becoming less urgent to do that. So I think it's more and more accepted now that it's, in a way, just another numerical tool in our toolbox, but shiny and neat one. And there are many questions how to best employ it. So that's the umbrella of this topic, and in particular, it again applies to the diffusion modeling aspect of it, where we're again facing pretty exciting new technology, and it's not yet clear how to best employ it. We are, my group, looking at fluids a lot. So here are some examples. I hope the video plays. There's a bit of rising smoke or splash of water. The flow around an airfoil is a classic example in this context. So it affects all of us, the air in the room you're sitting in, the glass of water on your desk. All of these are important processes. In the context of diffusion models, it's interesting to look at uncertainties. So going away from the completely deterministic viewpoint, and the classic distinction we can make is between aleatoric randomness, so the ambiguity of processes, and uncertainty or undeterminedness of solutions, and epistemic uncertainty, which is given a model, the errors and approximations it makes. And yeah, a good thing to keep in mind is this epistemic uncertainty we can reduce with better models or more data. The first one is something that's inherent to the process we're looking at. And so I'll mostly be looking at the first one. The second one, in a way, is also a fundamental question for many of the learning algorithms. But in the following, I'll assume that we have some more or less aleatoric process, fluid simulation that's underdetermined, that we want to look at. And in this context, we want to know what are possible solutions given uncertainties, say in a measurement or a specification. And we want to obtain these solutions with the help of deep learning and differentiable simulations, which I'll come back to later on, actually. So this is a basic setup. And diffusion models are also worth at least a brief overview. In case you haven't heard about them, right? We're looking at a process that basically destroys the information. So we have, this is borrowed from one of the famous papers in the field. We have some signal, say an image, and we're destroying it effectively by adding more and more noise. And then we're training a network to learn the reverse process. And turns out this works surprisingly well. In the context of the following simulations, just to briefly introduce a notation, we'll have some quantity of interest, some y bar that's computed by some function f, and we want to approximate this with the neural network and weights theta, so we have some approximation y for simplicity without the bar, given, say, a surrogate learned model. Could be optimized with some loss function, say an L2 loss. And for these diffusion models, we now introduce this Markov chain of noise that has a virtual time with respect to this evolution or the application of the noise. But yeah, that's not a physical time per se. This is a construction that we can make, and the learning goal in this context for this reverse process becomes to undo the noise. So here we can, with the subscript R, introduce some time step that goes from the completely destroyed state, complete noise, and tries to go back from this to the original signal. What you'll see here is we basically get a weighting of the previous state, YR, some update from our network in the space of the solution, and then some noise, MZ. And in the end, at step R equal to 0, that's Y0, this should be as close as possible to the solution Y bar. And yeah, turns out there's some very nice theory behind these diffusion models. The factors here, alpha, beta, are simplified, but if you do it right, you can actually just work with Gaussian noise. Very simple to compute. That's computed with respect to a fixed schedule over the course of these steps, and networks can actually learn this. One of the main implications is that now we don't have a deterministic one-pass process that just gives us the answer, but this f theta here, the neural network, is potentially applied many times to give us the final answer.
So
that's also slower. Yes.
Is the noise coming from the approximation error of the neural net?
No, this is for the diffusion models. It's really something we introduce. So
what is it? Or is it the information loss of the diffusion process itself? Why is there a noise?
Sorry, for the diffusion models, it's just completely artificial. You add noise on top of your original signal. And then in the context of the...
I guess I'm trying to figure out what is it trying to model. Or is it the measurement noise of the like measuring the diffusion process?
In this case, this is the basic diffusion model setup. So here it's completely artificial. The noise actually does not really have a meaning.
Okay.
So I'll come back later to these to the connection to the physics settings, and then you're right. Later on, this could actually model measurement errors or uncertainties in a state or in a measurement.
Okay, got it.
Although how to best specify that or how to best model certain real approximation errors with this noise is actually an open problem. We also typically just treated this quite in a fairly simple way. But the noise here has in a way no physical meaning. It's really just
makes sense.
A helper. Yeah, and okay, I directly want to skip to a nice graph to motivate a bit that this does make sense. So this is actually one of the results that one of my students came up with in an upcoming paper, and that also convinced me that there's something that really works. So we've tried, or if you follow the field, there are different ways to work with uncertainties in deep learning already. So these diffusion models are not the first thing that you can try. We, for example, experimented with Bayesian neural networks for quite a bit. And here we now have a fairly simple reduced 1D turbulence case. And it's really just 1D. So along X here, you can see a range of Reynolds numbers, which basically are a measure of how turbulent a certain flow is, from pretty relatively simple and more laminar to quite chaotic on the left side. And basically, with increasing chaos, we can compute ground truth solutions, and we know that the statistics change, and it should become more and more chaotic, which shows in the standard deviation that's shown here along the Y. So this is a ground truth data set that is very simple in a way, but has a varying standard deviation and a varying content. And right, so the one very classic way to do this is to use a heteroscedastic model, which means you really learn mean and standard deviation. The black curve is the reference, by the way, and the blue one here for this heteroscedastic model approximates it quite well. But here you're imposing a very strong prior already on the solution. So here you really just learn mean and standard deviations. So you actually don't get good samples out of it. because right, if you try to draw a sample, say of some spatial field, it's going to be very noisy. The model doesn't know what correlations in a certain data set. And the orange curves here are these Bayesian neural networks, which internally need a weighting factor for the uncertainty. So it's a KL divergence. It's computed internally and has a coefficient, this lambda, that you need to choose. It's not clear how to choose it in a general case. And as you can see here, the different orange lines, depending on what you choose, you just get different standard deviations. So essentially, you manually or indirectly just specify how much variance your solutions are going to have. It doesn't learn it. This doesn't really work. And the red line shown here, pink red line, is this DDPM, the diffusion model. And it also does have some hyperparameters, but they're less central. And basically, once it's set up in a way that it does learn the solution well, that it converges, it really captures the change of standard deviations, and it can actually produce good samples in the end, which I won't show for this case. I have some other examples in a moment. But in a way, as an introduction, this was one of the first results also in my lab that really seem to indicate here's a method that can actually work with distributions and figure out what these distributions should look like for different inputs. All right, so I quickly want to visualize the different approaches here just for clarity. So a normal network would just do a one-pass deterministic production of some output. If we have this heteroscedastic model, we basically produce mean and standard deviation. Then we can sample afterwards, but typically this just gives noise. For the BNNs, it's a different process that actually samples the network. So here we kind of learn the distribution for the network structure itself, draw a sample from this, and then have a deterministic pass that produces an output. For DDPM, in contrast, we have this noising process, this Gaussian noise from before, the Z, that is applied repeatedly and that the network tries to undo. So here we have something iterative that uses the noise and has a stochastic component in an iteration. So that's good to keep in mind. So here we have something that should be indicated by this dashed arrow that is iterated, typically on the order of 100 times or so. So it's much more expensive, but uses this noise as part of a repeated evaluation of the networks. All right, so I've just shown this graph without much detail. It's the first indication where we can quantify a bit what the distribution should look like, that this works. But to come to a slightly more interesting case, we also looked at this for temporal evolutions. So now we have this noising process and its reverse for a whole time sequence. And we are really now learning this diffusion model that is applied many times for every time step of the physical evolution. So we have this noise evolution, that was previously called R, and now we have a second time that is a physical time, that is the evolution of, say, a fluid or some physical phenomenon. So that's important to keep in mind for this version. In a way, we really have two time scales, the physical one and the unphysical noise time. So for every time step, we basically run through this whole denoising process. And interestingly, that turned out to have very nice properties for stability. So in a way, the model, potentially due to learning to deal with all this noise, produces very stable updates, even if it's not trained for very long rollout length. So what turned out to be quite important here is, of course, a bit in contrast to classic generative models, we, for a temporal process, want a very strong conditioning on a previous state. We have some global parameters, but also it really should be the evolution of some system over time. And hence, we basically need the diffusion model to strongly take into account the previous state in order to produce the next one. And just to give an overview of how that works in the training process, this is also actually taken from previous work, but it's relatively simple to do. You can train the state called D for data here and the conditioning C together, that both of them run through this noising and denoising process in the same way. And then at inference time, when we have a trained model, we still run the whole backwards denoising step for the data part, indicated by the red arrows at the bottom here. But the conditioning is fixed and constant. So the network actually produces this, but we discard it and just compute the analytic state with the correct amount of noise for this Markov chain, and then keep on running the model on this combination. And that actually works quite nicely. So basically, because this noising process is controlled and we know how the noise changes over the course of these iterations are, we can input the condition in an analytic way.
Okay, so just to understand kind of the approach, because it seems like a good summary. So when you say you have a what's called neural surrogate, that sounds like the more classic one. I predict the next time step from the previous time step, and there's no noise there. So when you say a heteroscedastic model, that I'm not familiar with what that flavor is.
Okay,
building up to this thing.
So that would mean that if you imagine you have a state of your system, a velocity field or so, that would give you a mean and standard deviation for every velocity sample in your output. So it's sometimes useful to know, right, here's a region that could change a lot, but basically to get a real velocity field, you then need to draw samples from the distribution, and it's pointwise. So every sample point in a field could get arbitrary values within that distribution, and typically they're very noisy.
So you're not capturing the correlation between nearby. Okay, so the way I should be thinking of heteroscedastic, because I'm actually not following how that captures time evolution, right? Because you have a distribution for every point. What about next time step?
Right. So it would only capture this imposed distribution on every single data sample or every component of a vector, basically, your velocity vector.
Okay, so when you were saying that that looked like they had good accuracy in the previous plot, that really it's a good summary of a snapshot of the simulation. It is not the simulation.
Right. It basically really just learns mean and standard deviation, but not how real states look like. Okay.
And then so the Bayesian process. So what was your model there?
Okay, this is
the Bayesian neural net.
So the Bayesian neural networks are another pretty popular. Actually, in the last years they were, I think, before diffusion models, very popular. So the idea here is that you learn a distribution for the weights of your network. So every weight theta of every conv layer or fully connected layer gets a mean and standard deviation. And then in order to run your model, you actually sample from this distribution of your network weights. You get one specific model, and that produces your output.
Okay, so really, it is essentially neural. It's trained the same way as a neural net would be, except now you have a bunch of samples and have a Bayesian distribution from which the neural nets are sampled, like neural surrogates.
Right. It's typically trained with some tricks like dropout, or there's some flip out layers that compute some these updates for the weights. But essentially, you get a distribution on your network itself.
Good. So now I think it's a good time to understand this thing, because here I kind of get lost because it looks like it's actually has the same flavor of a hierarchical Bayesian model, where it seems like you are having multiple layers and you have refinement, and then you have backpropagation through it, like you kind of go up and down in terms of hierarchy of refinements. But I'm not sure if that's a good summary.
You're right. I think it's better to think of it really in terms of time steps for this noise that was shown in the beginning with a noisy image. So also, if you think about trying to get one next velocity field, you would basically start with a completely noisy state again, condition this on the previous velocity field, but tell the network to, from this noise, produce the next evolved velocity sample.
Okay, so fine, it has an error. So then what's the refinement process?
And the network then gets this noise, and over the course of, say, 100 steps, there's typically also some fixed decay to reduce the noise.
Steps, you mean physical time or refinement steps?
Refinement steps.
Got it, okay.
These virtual noise steps. The network, that's what's been shown in diffusion models quite extensively, can learn very well to handle this reduction in noise and get some real sample out of the noise.
Okay, so first of all, somebody's asking, is this paper published? Because I think they're just looking online.
This paper is not yet published. Another one is published, but this one should be on arXiv soon.
Okay, I have to
unfortunately, this is in the works. Should be on online soon, but
okay,
not yet up.
Okay, so yeah, when you push it, I send it to me a link. So then, yeah, moving on with this. So what I'm gathering right now is I'm hearing a backpropagation step where you have the next time step is conditional on previous time step, and then you have the error when you backprop, but you Bayesian backprop. It sounds a lot more like a posterior calculation.
So in this case with the noise, it's definitely a Bayesian it's a Bayesian viewpoint. But for the network, it also works very differently. It's really a denoising step. So the network has the goal to reduce the noise and give you the real answer. And the network also actually does get this time. It knows where in the evolution it is, whether it's a really noisy state or a less noisy state that's close to the final answer.
So I guess that's the key insight here. I'm not following. I guess how is denoising different from posterior calculation?
It is a way to compute the posterior, to compute a sample from the posterior. So that's what the network is trained to do. You have a posterior distribution, and the network has a goal to turn the noise sample into a sample from your distribution.
But that's what a Bayesian neural net would do. Unless
yes,
yeah,
that's differently though, right?
What's the difference? That's the key insight. It seems like.
Right. So okay, it's a good question. Let me quickly go back to this.
Oh, and Kevin, meanwhile.
Hey, Greg, maybe we should take that offline. I think Bayesian neural nets is a completely red herring. Nils just showed that as a baseline to show it doesn't work well. Yeah. It's got nothing to do with diffusion models.
Yeah, so maybe to understand the diffusion models. Like, what exactly is the key insight of this work?
Yeah, so the BNNs is I don't think it's worth spending cycles on because the new stuff is all about diffusion models.
Okay, yeah.
It's really didn't work too well, and so I think maybe I'd be happy to discuss with someone later if you're interested. But the BNN gives you distribution on the network, which turned out to not work so well, and the diffusion models iterate on the state with additional noise and do this many times to produce an answer, and that works really well. It's stable training wise, so network is in a way trained supervised for individual steps, and it then turns this noise into a solution, and that's on the slide I just had here. Oh yeah, here.
Right.
So maybe if you can just clarify, make sure check my understanding. Are you saying that you basically would at kind of training time, you'd train to basically learn to generate or denoise both, let's say the kind of conditioning, the past time step and the current time step, and then at inference time you would kind of actually add noise to the conditioning, the past time step, sample noise for the current time step, and then diffuse them both?
It's slightly different. So what we did here is you could imagine that you have say an image or some field with two channels. One is the next answer you want to get. The other one is a conditioning, the previous time step or some boundary condition or so. And then in the training process, the network would actually learn to produce both of them. Also the second parameter so that you give it. And at inference time, you would let the network produce both of them, but throw the second one away.
But the initial condition for the at inference time, which would normally be IID noise, say, like as in at max diffusion time, is the second frame generated by actually adding noise to the conditioning.
Exactly. You take the ground truth conditioning, and you would know I'm at this time step. It needs to have 98% noise, exactly, and then you could guarantee that you have the right.
So that's, I think, as far as I understand, that's kind of different to a standard conditioning where you're kind of every approximation of the, every calculation, every denoising step would be trained to take a clean version of or just some kind of standard version of the conditioning. Did you try that? Is this preferable for some specific reason? Maybe the kind of strength of the conditioning or the time continuity that you need?
We did try a bunch of other ways for quite a few of these models. Basically, in the transformers, right, in the attention, you can bring in the conditioning and make sure that it's present and kind of also throughout the whole network applied. But in the end, we had the best results with this relatively simple approach of really conditioning only in the input and with the pre-computed process.
Great, that's very interesting.
I don't think we've exhaustively tried all of the variants there, but in the end, it worked nicely.
Thanks.
Oh, and Kevin?
Yeah, can I ask? So I'm familiar with diffusion models for image generation where it's on a 2D grid. Are you, and that's usually like a single snapshot, right? And people also work on video generation, which obviously is a temporal process, but it's often generated in one chunk, like a 3D cube, as opposed to autoregressively. But there is interest in generating, like at Google and elsewhere, in generating long-form video in an autoregressive way, so it can sort of grow unboundedly. So can you, I don't know if you have any visualizations of the kinds of simulations you're generating. It looks like they are, okay, this will be very helpful to ground it. Thank you.
That's a very good question for the next slide here, exactly. So it's autoregressive, and that's also why we found it interesting, because for videos it's not so common. You're right, it's typically chunks, or although there's some works that also with some clever conditioning have these infinite videos or very long ones. So it's a bit related, but we're really doing it autoregressive time step by time step. And here you can now see one specific example in the top left corner and 5 different samples from this simulated posterior. And this is now basically a high Mach number flow simulation. So it's almost on this boundary to being supersonic. So it has shock waves that influence the flow. And especially there's an obstacle that is actually not shown. It's some round cylinder you can imagine. And around it, you can see these shock waves. I hope this shows up in the... Oh, does the video play? I'm not sure. Let me play it again. It's a fairly chaotic flow. And here, all simulations start out with the same first state and then have the goal to produce next ones. And these different ACVM samples, which we dubbed the diffusion model here, do actually lead to plausible states over time that vary quite a bit. I hope this shows in the last frame. Now you can see this is after 100 frames, I believe. The states look quite different, but they're all actually realistic, which you can also, in this case, evaluate with some statistics. Different ones to be computed. Here's just the velocity magnitude, but also in terms of the energy cascade and other metrics. This does work quite well. So these different posterior samples seem to capture the expected distribution of the states quite well.
Kevin, you had a question?
I was actually going to ask about these metrics. Like, how do you know it's doing well? But you already mentioned it. Like, this is a key problem in like video generation because it's
right.
It's semantic. There is sort of no notion of truth. But I guess you have physical quantities that are meaningful.
In
You
a way
can
that-
derive from the samples, right? Yeah.
Here it's in a way easier because these are fairly standard test cases. You know what the distribution should be. Then you can evaluate on the posterior samples or on some ground truth. Right, for videos that would be much more difficult to compute.
Right, and I'm noticing now, I think, that the key insight here is that you're conditioning on the prior, your Bayesian stuff conditions in the prior state, whereas in other Bayesian stuff, you don't get that extra dependence.
So you could also condition a BNN on the previous state. You could actually treat it in a similar way.
Would you get the same results, or is that?
But it doesn't work so well, yes.
Yeah, the point is it's not a deterministic decoder, right? Greg, it's like,
Yeah.
so it's a Markov chain in physical time, and then each time step is a Markov chain in computational time, in simulated time, as opposed to a one-shot model. So it can handle multimodal distributions better.
Yeah, it sounds like the KDA then becomes the iterative refinement, which is not present in other approaches.
Exactly.
Okay, good. No, that's key. That iterativeness. I mean, this is also common in giant linear solvers. The iterative refinement is huge.
Exactly. Yeah. Exactly. The most classic solvers do iterate internally, and now these networks actually, in a way, move a bit closer to these classic solvers.
Great. That's very helpful.
Yeah. That's a good keyword. So we compared to some learned baselines here. Yeah, might not be too exciting. So, well, it's still good to know, I guess, that we tried some transformers, which we also spent quite some time on to tune it. They typically work in a reduced state. We didn't get those to work similarly well. And a simple UNet, if it's trained the same way as the diffusion model does very badly on the top bottom left side. It basically loses the cylinder. Although you can actually should also say, for fairness, the UNet you could more easily unroll. So you could train the UNet with seeing more of the time evolution, then it would also do better. But nonetheless, interestingly, the diffusion model, so this is actually the second one on the left side here, really keeps the stable and very good predictions without seeing essentially more than a single of these denoising steps. So we found this quite interesting, that it's very stable despite not being unrolled over time. Yeah, so that's basically the first part of my talk. Here we worked with simulation data, of course, but we didn't have any simulator in the loop. So they're very stable, do enable this posterior sampling. They are a significant factor slower, although that's also a bit of an open topic. So nonetheless, potentially at least an order of magnitude slower or so than a deterministic one-pass model, which nonetheless gives you this posterior sampling capability. So if that's interesting, I think it's still interesting application-wise, but definitely more costly. So what we before worked on a lot is to actually get simulators into the training loop. And the main idea is to have a simulator that works on some states S, and we rely on this simulator to actually give us a gradient. Same as for all the deep learning operators. We want to know, changing an output, a linear approximation, how do we actually need to change the input to get the desired direction and change. And this did work nicely in the past. You can chain this together just like normal backprop in deep learning. If you compute some loss function and you apply this physics simulator, say, between a network and your loss, then you can just combine the gradients to get an update with respect to some neural network for learning. The theta, again, denotes the weights of the network here. So in a way, from a deep learning perspective, this is not too surprising. It's not that widely used in simulations because of all the classic codes, but nonetheless, it is actually an interesting tool. And now don't want to talk too much about the basics here. The nice thing is, because it's so similar to what happens in deep learning, it actually allows you to merge the processes, the simulator and the learning quite tightly. And this has worked very well for variety of different things in the past. So I should mention there are actually different names in a way. This is classic, also joint methods that could be applied here, reverse mode, backprop, essentially, they're all the same thing. And a nice way to think about it is this Thinking Fast and Slow book from Daniel Kahneman that was brought up quite a bit by people like Joshua Bengio and others for looking at learning itself. I think it's in a way also a nice picture here, because I think in a way the simulator gives us a stable basis. It's like what here Daniel Kahneman would call a system 2, some analytic slow process, and the network can learn a more intuitive and fast correction of that. And for simulators, then we might look at this, say, over time for a whole chain, and along the way for every step of the simulator, the neural network would go in and help out and correct the solution and the states that we're getting. Yeah, so just to put this next to the previous approaches that I talked about so far, if we're just looking at bringing the solvers into the picture, there's no stochasticity. So this is now, again, a completely deterministic process. We just have some, could see it as an operator, the simulator that doesn't have any learnable parameters, that just transforms the state with respect to some PDE that we impose as prior knowledge. And this does work quite nicely. So we can actually make the solver and the neural network work together quite well. It's been done in quite a few works, but here's just one example from my lab. I looked at a learned turbulence model for a classic shear layer case. Also flow moving different speeds, and then you get vortex shedding with a specific frequency, and we intentionally now under-resolve this with a very rough solver and let a network improve the solution. And again, because this is a classic case, we can now look at the statistics. And here, the reference are now these orange dots. The basic solver is the blue line, and different learned variants are the green ones. So the energy spectrum for turbulence is this very classic quantity to look at. But here the picture, well, see the green ones are closer to the orange ones already, but there are not so many differences. If we look at different quantities, it becomes clear that unrolling, so actually letting the network see many of these steps helps. So here the bright green line that also matches the orange dots here on the right side very well is a model that was actually unrolled for 60 steps, 60 time steps at training time. So really the network gets a gradient through 60 steps of unrolling the physics and back propagating through all of them. It's costly, but this seems to give the networks information in terms of weight updates that know about how the system evolves over time, and that does help to capture some of the more subtle parts, like these Reynolds stresses that indicate the amount of mixing in the flow. And in general, the solution improved quite a bit for these cases. And now, also having these established statistics, we can now go in and say we take our DNS, the ground truth, and lower the quality with respect to these metrics until it's on par with the learned solver. Then we can make a relatively fair comparison about the performance. So here, for our solver, we had it on the same hardware with the same GPU support, and the network is nonetheless still more than 10 times faster when matching the level of accuracy. So that's a nice speed up. Although, of course, it's always a bit tricky to compare the performance across different implementations, but nonetheless a promising number. Right. So
in this case,
yeah.
Just to capture this, it's the simulation itself is learned as well. Like it's not just the gradient is learned, and the input is like longer and longer stretches of time steps of the original simulation.
Exactly. So now there's always some rough, potentially faster simulator in the training loop that works with the neural network to predict the physics, and it's unrolled for more and more time steps, essentially, like just predicting more and more time ahead.
And then the classic performance number, but the performance trade-off is also how many times you have to run the simulation in order to train it. So what's that trade-off?
So I think that's a good question. I don't have the exact number in mind. That's on the order of, it's actually order of magnitude more, probably closer to 100 than 10 times. So it requires a fair number of training data. This only pays off if you can be sure that this trained model is going to be used a lot. So for single cases, this will not pay off. Only if you're sure this is a case that you need to solve thousands of times or so, then this might be attractive. But I think, or I guess also the hope, especially for these turbulence cases, is that once we have a really good turbulence model, this behavior comes up in many other scenarios, then potentially this could be used a lot. But it's definitely expensive. And also these unrolling steps just linearly change the training time per update of your network. If you unroll 60 steps, it's actually 60 times as expensive as unrolling one step.
Okay,
so
yeah, that makes sense.
Another factor on top.
The amount of data is 60 times more than the input vector, right?
It's actually the same data. You can train on the same data, but for every data point, you basically go 60 steps into the future and compare across all the samples.
So you're predicting 60 steps into the future.
Exactly. It's really predicting.
And so your loss function is a lot more informative because it's like long-term predictive accuracy.
Exactly. The loss is then computed for all these 60 states, and that tells you how would I have needed to change something in the very first state in order to match something later on. This information comes into the updates here if you do this. And
got it. Thank you.
Typically does help stability, and but it's costly. It's compared to supervised training or so the long unrolling does require resources. So that's why we're talking about it. It's the nice thing though is that you only need this approximate solver in the loop. So the reference can be pre-computed in these cases. The data set could be something external and relatively costly that's produced once. The training time, you just need to run the solver that the network needs to work with, which hopefully is a fast one. So it's not as bad as running the ground truth reference solver many times. That would be prohibitive, but nonetheless, it's definitely also not cheap. Supervised training where you can rely on the data would be a lot faster. Also should be mentioned.
Oh, yeah, thank you.
Yeah, so we looked at this for reactive flow or also plasma simulations. This typically does work quite nicely, but now I want to come back to the diffusion models, which is actually now slightly tricky and changing the picture, but nonetheless, it nicely puts the two components together, I believe. We are again looking at the diffusion process over time. And here this is drawn for a simple physics case. And now, in a way, similar to before, we have some process, the solver, that gives us updates over time. We can actually see it as a drift in the diffusion models or this stochastic perspective from before. And then we have an update from a network that work together to undo noise and picks up to basically improve the solution we're getting over time. So in this case, P is still the physics, and this S will be the corrector. So this is actually better to look at from the score matching perspective, which is also kind of a diffusion model, but motivates us from a different angle. And one of the main differences to before is that now the physical time and the noise are actually linked. So now if you would want to, like your question earlier also, if you would want to apply this in a real setting, it would be important to actually model the noise that is introduced for every step along the way to validate this or match it with some observation noise or some uncertainty in a simulator. So now basically this Markov chain and the simulation are linked. And that also means that the signal is never really completely destroyed, but we're looking at noise that constantly perturbs and influences the states of the solver. In this context, we can use these differentiable solvers, very similar to the process before, and train them together with a noise step in an iterative way, and also unroll over multiple steps potentially, and nonetheless get these probabilistic modeling from the diffusion models, which the previous turbulence example also did not have. This was a deterministic model, and this actually does work quite nicely. Let me show this with just to mention the underlying equations. So now we're looking at some evolution of some states, these x, for example, with a physical drift, as you can see it. We can see it as a kind of drift, the physics solver, and a noise term z that is scaled with some function g. So we have a stochastic Euler step here, and with the score matching, we can turn this into a reverse update where you predict a previous state t that undoes the noise using the gradient of the score here, this middle term now, and again a certain amount of noise that is also introduced in the backwards chain. So in a way, this is now using these score matching viewpoint. And if you're interested, right, also this is a paper from another PhD student, Benjamin. He actually did a full derivation that this does make sense, that you can see the solver as a drift term, and this still adheres to the typical score matching formulations. And this paper down here, these inverse problems with score matching, this is actually on arXiv. Anyone's interested, I can post the link later. Yeah, so to start with a toy example for this, we can look at basically a very simple function that starts with a sine and then denoises this information and lets the sine decay and turn into noise around 0. So that's what's shown on the left here. We start either at 1 or -1, and over time, shown along x here, this converges to 0 and becomes very noisy and indistinguishable. And the score function now, a bit similar to the diffusion examples before, has a goal to undo that process and from some noisy sample around 0, retrieve one of the sine -1 or 1 values for a given time horizon. And it's a very simple case, but you can train this neural network here to represent the gradient of the score function to give you an update here. And the nice thing of the simple, very simple scenario is that if you train this with a one-step training, it actually does stay relatively noisy, and you get trajectories that explode in undesired, unexpected ways too early on. Whereas if you introduce this unrolling, you're basically training over multiple steps, the signal does become more stable, and also the updates from the score function basically give the more consistently recreate the different sine values. And yeah, this is of course just a toy example. We looked at some maybe slightly more complex cases. So here we are admittedly also still away from these full turbulence simulations or so, but the heat equation is an interesting case because this effectively does diffusion and actually does, from the physics, destroy information. So we're starting with what you can see on the left, some relatively detailed Gaussian random field, apply a diffusion process over time, which blurs out the solution. And if we now try to undo this with the physics, because inverting diffusion is unstable, if we directly invert this, this blows up and does not retrieve the right answer. If we now train it with the score matching approach, we can actually leave out the noise to get a probability flow, as it's called in this context, or we can apply a certain amount of noise in the variation, also in inference time, basically, and then we can get retrieve an answer that is quite close to the ground truth and also does capture the noise that we would expect, or the smaller scale details of the initial solutions. Yeah, another example that we looked at here is a slightly simplified flow setting. So this is isotropic turbulence, but now with a learned update. So I've talked about this physics step before. This could also be a neural network where we, by construction, have a differentiability. And also in this case, this does actually work quite nicely, although when combining such an update and this diffusion process, we notice that there's a bit of a trade-off between the deterministic variant without the noise that gets the mean error retrieves a very good solution in terms of the mean, and this stochastic variant that does a full SDE with noise that can also capture smaller features at the expense of a larger error in terms of the mean signal. That's what you can see here with the two green bars in terms of MSE and spectral error. But nonetheless, this works with relatively complex cases and now actually does this combination of a differentiable solver and a diffusion model. Yeah, so this is work in progress, but I think it's still an exciting direction. So I was able to show a bit that this does make sense, that this combination of diffusion models and simulators, especially if the differentiable is a nice direction.
So actually on that, because I mean, yes. Experimentally, I could see that, but I guess I'll try to get the key ideas of kind of the bits you tweaked, because there's the score matching. I want to understand how much intelligence is required, like domain-specific intelligence, as well as the Bayesian as opposed to deterministic, to what extent that was instrumental. And finally, the fact that you're looking so many time steps in the future, how much was that responsible for the better results?
So we do compare this to the deterministic networks in the paper. I think that for this case, it's not a good comparison. But in general, so if you have a deterministic network, the mean is at least as good. So retrieving the mean signal does work quite nicely. But what's missing again is this posterior sampling. So by introducing the noise here, you potentially get the capabilities for restoring different modes or different solutions. And I think this is actually also, or maybe even especially for inverse problems, which are potentially under constraint. So there might be maybe different modes in your solutions, or different structures that give you the same answer or that match the same observations. And this is really an interesting component.
So where mean is not a useful metric, it doesn't matter that
exactly.
You the mean well. Got it.
Exactly. The mean sometimes could be a pretty bad approximation of a real solution.
And then score matching. I guess to what extent was that instrumental?
The score matching was instrumental in the sense that also what I think is one of the important parts of the paper is that there's really a theory behind it where you can show that this is a proper formulation that captures the distribution as specified by the data. And potentially this might also be possible with the classic Markov chain view of the diffusion models, but we found this works actually more nicely, more straightforward with the score matching viewpoint. So I think in a way this is the first, as far as we know, first derivation of actually matching some physics operator and these diffusion models, or bring them together. And we found the score matching viewpoint to be more natural in that context.
So should I think, because it seems like a reusable idea here, should I be thinking about this as you're using like human intelligence or the basic mathematics to dimensionality reduce the dynamics of the underlying physics to a much lower dimensional manifold, and say, whatever you do, yeah, it wouldn't be accurate, but stick to this manifold as well, and that's an unusually useful manifold.
That's a nice viewpoint. It's difficult to show, but most likely that's what happens, that the network finds some reduced manifold where these solutions are smooth and can be captured, and also where different perturbations in terms of this noise give you valid samples. So where from slight changes, it can actually learn to recover different spots on your solution manifold.
That makes sense. Wait, and I see a question from Elon Price. What are the efficiency implications of diffusion and real time being the same, and thus only needing to be autoaggressive in one time?
Very good question. So the nice thing about this setup is that it's not more expensive. It's essentially the same as doing this regular learning process. You need to compute a bit of noise. The network is mostly in line with previous approaches. So you're saving this whole Markov chain for every step along the way. The disadvantage potentially is that you cannot deal with really strong stochasticity. So the solver actually needs to work also with potentially noisy signals, and your network only sees a certain level of noise. My guess is that we haven't looked at this in more detail yet, but that you limit it in terms of the randomness. If your solution is extremely diverse, I could imagine that this limits the expressiveness of this generative component. But it's nice and fast again.
Yeah, makes sense. Thank you.
Yeah, no, to just briefly give an outlook. One topic that we're looking at in my lab, which I find quite interesting, is we have a small fog machine that's captured with a bunch of cameras and produces these puffs of fog. It's some dissolved oil in a controlled manner, and just with a few views, it's very, very under-constrained. So we do have some classic reconstructions of this, but examples like this and also scaling this up to more complex, high-dimensional inverse problems, I think there are a lot of interesting directions here, and I think it's definitely an exciting time for research. A lot of interesting questions and open avenues to explore. I should mention we have this website that has a lot of examples about these differentiable physics approaches. We're working on an update for the whole stochastic modeling part with diffusion models. Those are not yet properly integrated, but nonetheless, especially if you're interested in the differentiable physics, please check out the website. And otherwise, thanks for listening. I'd be happy to answer other questions that might have come up.
Any questions on the call? So then I have one that was really spawned by the final example you had. So it seems like part of your philosophy is you have a fairly limited number of simulation runs of the expensive simulation, and then you back out your approximation. And I'm guessing it's naturally, well, they can just be your data sets. So the obvious implication is I have another one of those systems which has very few samples, like the climate. The Earth has not been going through it that often, or any kind of economic data sets where they're all very interlinked economies. There's only so many countries in the world. Again, not that many samples of a very complex dynamics. So what do you think is the promise of these methods for that?
So to be realistic, what we've noticed is that also from the diffusion model, you get these nice stochastic capabilities that you can get multiple solutions. They seem to work really well, but whether it's really much better than a single deterministic prediction, I wouldn't say. I think the strength is really if you have multimodal distributions, then it's pretty crucial. Unfortunately, our hope also was that this might work especially well if you have very little data or so. But it didn't fundamentally change the picture. From our experience, it requires a similar amount of training data to other, say, supervised learning approaches or the differentiable solver. So unfortunately, this combination I discussed here, I think doesn't pay off in a huge way. However, what I think would be exciting to explore here is what's also happening with all the large language models, to have some pre-trained, really powerful pre-trained model that you could fine-tune. I think that could work.
So actually, let me just ask you another one. It has been observed that surprisingly many differential equations are first order, second order, no more. There's only so many kinds of dynamics. So are there such common, not language models in this case, but yeah, common physics models that are plausible?
I think there's definitely potential. Would be worth a try. We looked at this in simpler settings. In the past, it didn't work so well, but I think with the advanced all the transformer architectures and these lowering approximations for language models, I think there's potential for picking that up again.
Thank you very much, Nils. This was fascinating, very valuable.
Great to hear. All right. Let me know if you have questions afterwards. Thanks for the invite.
Thank you. All right. Have a great rest of your
Have a good
day.
day, everyone.
Bye.